All right. This lecture will cover the sixth and last property of the liquid state that we're going to talk about, which is freezing point. So freezing point, as the name suggests, is the temperature at which a crystal lattice forms. A crystal lattice is, of course, the solid structure associated with whatever compound that you're talking about. Now, of course, you know the freezing point of water, right? For water, the freezing point, the normal freezing point is going to be 0 degrees Celsius. So that's normal because that's the freezing point at 1 atmosphere of pressure. 0 degrees Celsius or 32 degrees Fahrenheit is the freezing point of water. So this is the temperature at which the solid forms. Now, there are a few thermodynamic definitions we should cover. I always find these confusing because of the names of them. There's the heat of fusion and the heat of crystallization. So the heat of crystallization is the one that makes more sense to me. So I'll actually start with that one. The heat of crystallization involves the transition from liquid to solid. So when you go from a liquid to solid, that's an exothermic transition. So heat is going to be released from the system to the surroundings. So the heat of crystallization is defined as the heat that gets released when 1 mole of liquid transforms into 1 mole of solid. Okay, it's a molar quantity, and it varies by compound. So the heat of crystallization of water, for instance, just to give you an example, is negative 6.02 kilojoules per mole. That negative is important. This is an exothermic property. Okay, when we go from a liquid to a solid, heat gets released. The heat of fusion is the opposite. It's the endothermic property. This is going to be the heat that you have to add to a solid to get liquid. Okay. I find this counterintuitive because the name fusion implies to me that you should be forming the solid, but fusion actually refers to melting the solid. I'm not sure why it's named that way. Heat added to 1 mole of solid in order to get 1 mole of liquid. All right, so I always have to double think these definitions. The important thing to remember is that the heat of fusion is the endothermic property, and it varies by compound. The heat of fusion of water, for instance, is positive 6.02 kilojoules per mole. So equal and opposite thermodynamic properties. Let's do an example where we use freezing point to figure out the energy involved in a phase transition scenario where we're also raising the temperature. So here we have to use what we know about freezing point, but we also have to think back to the thermochemistry chapter where we learned about specific heats. So can you calculate the total amount of energy that's required to raise 180 grams of ice at 0 degrees Celsius to water vapor at 100 degrees Celsius? Now, let me change that a little bit. I'm gonna say instead of to raise it, to change it, because it's not just raising a temperature. We're also undergoing phase transitions here. So there are many things to think about. I'm going to give you a hint for this problem. You're also going to need the specific heat of water. The specific heat of water, you may recall, is 4.18 joules per gram degrees Celsius. And this is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. All right. As with the thermochemistry problems that we used to do, to solve problems like this, you absolutely must consider all of the steps in the process that you need to undergo to make the change happen. I like to list the steps. what am I starting out with? I'm starting out with ice, which is a solid at 0 degrees. So I'm starting with a solid at 0 degrees Celsius, which is the freezing point of water. And what I want to do is melt it, right? It's going to become a liquid at 0 degrees Celsius. Unless I'm told otherwise, I am assuming that this is under atmospheric conditions. So pressure equals 1 atmosphere, and I'm dealing with normal freezing points and normal boiling points. So since I am already at the freezing point, the energy associated with this transition should be equal to the heat of fusion, right? The heat of fusion is going to determine how much energy it takes to melt that solid. Now, I want to go all the way to water vapor at 100 degrees Celsius. So here's where the specific heat comes in. I am going to take that liquid. I'm not doing a phase transition, but I want to heat it up to 100 degrees Celsius and then vaporize it. So I get the vapor. Of course, vapor is synonymous with gas, the gas phase, at 100 degrees Celsius. And I can stop there because that's what I want, the vapor at 100 degrees Celsius. So the transition here involves a change in temperature. Now, the phase transition from liquid to gas, from liquid to vapor, is going to involve the molar heat of vaporization. So what I want to do now is figure out the energy required for each step, because the total change in energy, I'm going to call this step 1, step 2, and step 3. The total change in energy is going to be equal to the change for step 1 plus the change for step 2 plus the change for step 3. This is kind of a Hess's law thing, right? We can add these changes together to get the total energy change for the process. So let's figure out the energy change for step 1. For step 1, I have the heat of fusion of water, which I gave you a moment ago. It's 6.02 kilojoules per mole. Now, how much water do I have? I have 180 grams of ice. Ice is, of course, water. The molecular weight of water is about 18 grams per mole, so I'm just going to round that to 10 moles of water. Okay, I need it in moles. I need the amount of water in moles because I need to multiply that by the heat of fusion to get rid of the moles. So 10 moles of H2O. I needed that in moles so that I can cross these moles out and get the number of kilojoules of water. So that is going to be whatever that is, 60.2 kilojoules. All right, now for step 2, I have the specific heat, 4.18 joules per gram degree Celsius. I am going to multiply that by the delta T, which is going from 0 to 100 degrees. Delta T equals 100 minus 0. So the delta T is going to be equal to 100 degrees Celsius. And that's how I get the 100 degrees Celsius here. And I also know that I have 180 grams of water. So this is going to give me some answer. The grams cancel out. The degrees Celsius cancel out. And that's going to give me an answer in joules. Okay, I don't have that off the top of my head, but you can put that into your calculator and get that product. Then the last step involves the heat of vaporization, as you can see right there. So the heat of vaporization, I gave you guys a moment ago, or you can look it up. If ever you need, you can look it up. 43.8 kilojoules per mole is the heat of vaporization for water. It's an endothermic property. And I'm going to multiply that by the 10 moles of water to get 438 kilojoules. Okay, now what you want to do, once you get this number, you have to convert it to kilojoules. And then you add all three of these together. And you should be able to find that the delta E total being equal to all of these steps is about 500. I'm going to round it to a whole number, 573 kilojoules. This number happens also to be the heat of sublimation for water. Okay, so I just made you calculate the heat of sublimation for water. Sublimation, of course, is the phase transition from solid to vapor. Okay, and what we did here was we took 10 moles of water and we started with ice at 0 degrees and we ended up with vapor at 100 degrees. So we broke that down into a stepwise process, but overall, the delta H or the delta E of that process is going to be referring to the change in energy required to sublimate that amount of water. Okay, so this is not the molar heat of sublimation. This is the heat of sublimation for the amount that we were talking about. All right, so I hope you can pause, go through, make sure you can do the math in that problem and everything, and that the arithmetic makes sense.